Welcome back one more time. In this final audio presentation, which I'm sure you're quite pleased about that it's the final. I'm sure you're good and tired of hearing my voice here. We're going to review the clinical trials, and then the exercise will be intended to reinforce this and expand upon it. Clinical trials, one of the things that we do is control things quite well, and sometimes we wonder if it's too much control, so it's not as generalizable. Here are some of the concepts we want to cover in the review: the design, appropriate use, advantages and disadvantages of clinical trials, also the biases, some blinding, what different types of blinding are, the confounders, how to eliminate them, and I know we've talked about this before, but we will review it because it's critical. Look at how increased control means decreased generalizability. We'll look at some common measures used in clinical trials. We'll touch on survival analysis because it's used oftentimes in these studies. Intention to treat, which is an important method to consider in terms of interpreting the results. And factorial, crossover, and meta-analysis trials as well as community trials. Clinical trials are truly experimental. That is, the experimenters decide who goes into which group. That can be done in a variety of ways. They might decide that everybody who comes into the clinic on Wednesday is in the group, or they may flip a coin, or they may use a computer to come up with a randomized list, which a simple randomization is the most effective randomization or the strongest randomization and eliminates confounders to the greatest degree. Advantages of clinical trials: it is indeed the strongest evidence of causation because there's no recall or selection bias and there's no confounders if it's truly randomized. You are able to describe incidence rates and attributable risk because these are prospective studies. The limitations include that these are expensive and time intensive, so they're not a design that you often want to go to initially. You want to start with cheaper designs first, and then if those show associations that you're interested in, then perhaps advance to a clinical trial that is more expensive. There is decreased generalizability generally with these because of the high level of control. There are some biases inherent. There's different rates of compliance between the different groups. Sometimes if you're giving somebody an experimental drug and then others a placebo and it's randomized, there may be effects of the experimental drug that are unpleasant and people may drop out of the study because of it. They also may cross over into the other group. So if you're randomizing surgery versus medical treatment and people get medical treatment and then get worse and end up needing surgery, for example, they may cross over into the other arm of the study. There are loss to follow-ups. These are prospective studies. You have to follow people sometimes for long periods of time, and you lose track of people. There's also diagnostic suspicion bias, like in cohort studies, and the experimenters, if they're aware of who's in which group, that can sometimes affect their judgment or their degree of effort in terms of monitoring or following for an outcome. Here are the different categories of blinding: single, double, and triple. Single blinding refers to just the subjects. That is, the subjects are unaware of which group they're in, and sometimes we actually test that by asking them which group they think they're in. And if the blinding is effective, then there should be an equal chance of them responding, I'm in the experimental group or I'm not. I'm getting the real drug or I'm getting the placebo. Double blinding refers to subjects and experimenters both being blinded. So the experimenters are unaware of which group the subjects are in to prevent biases on their part. And then triple blinding includes those doing the analysis as well. Here's an example of a clinical trial. There was a study published in 1993 looking at ultrasounds in pregnant women to see if they affected the outcome and therefore whether or not they were clinically needed. They looked at 15,000 pregnant women. They randomized to ultrasound versus none, and they found no differences in outcomes between the two. One of the things they did in this study, as well as other clinical trials, is to eliminate the possibility of confounders, which makes it powerful. So how do we eliminate the possibility of confounders? We randomize. And how do we know if the experimenter is truly randomized? It's important for the reader to know if this was done adequately. So how does the experimenter or the authors show you that they truly randomized? And this is done in what is usually a table 1. It's not required that it be labeled table 1. It might be the second table or third table, but usually it's table 1, and I'll show you an example of that. But basically what it does is shows you many of the measured characteristics of those in the experimental group and in the control group, and lines them up so you can see that all of the factors are the same in both groups. The proportion of males and females is the same. The average age is the same. Whatever it is that they measure should be the same between the two groups if it's truly randomized, including the number in each group, generally. This is the table 1 for the Wigman trial. You can see the columns for those in the ultrasound screening group and the control group, the absolute numbers as well as the percentages in parentheses. And you can see that they're virtually identical, as they should be, if the two groups were truly randomized. And this convinces us, the readers, that the authors or experimenters did a good job of randomizing. Now, occasionally there is a difference between the two groups in one or more of the measures just by chance. If you look at enough measures, you may find some that just by chance end up being different between the two groups. So you might find that the smoking level is different between the two groups. It's not in this case, but if you found that, then you would want to keep that in mind when interpreting the results, because you have identified a real difference between the two groups that might affect the outcome. This randomization and this evidence of an effective randomization is really what makes the clinical trials generally so very powerful, and that's why it's important for the authors to include this table 1 in the study write-up so that we, the readers, can see that and be convinced of that. Here are the entry criteria for the Wigman trial, and this is important to understand in order to know whether or not this trial would be applicable to your own practice or your own group. They, for example, looked at these pregnant women, and they wanted them to be more than 17 years old, English speaking, last menstrual period known within 1 week, gestational age less than 18 weeks. They had to have had regular menses prior to getting pregnant, and they had to be off oral contraceptives for at least a month prior to getting pregnant. Now, these factors in practice, for example, that I was in prior to the one I'm in now, most of my patients would not have qualified for this study. Probably 90% of them would not have qualified for this study because most of them didn't know their menstrual period within a week. They were frequently under 17 years old. They had irregular menses. They were on oral contraceptives right up until they found out they were pregnant, etc. So this is very controlled. And if it doesn't match your population, it doesn't matter how valuable in a way the outcomes or the information gleaned from the study is if it doesn't apply to your practice. So if your patients don't fit, then it may not apply to you. And that's the generalizability. Does it generalize to your practice? So you need to look at the inclusion and exclusion criteria of clinical trials to see if they're applicable to your practice, if they really fit. So this is where you can possibly control too much, to the point where it's a strong study in terms of efficacy, but doesn't generalize to the populations at large. It's not real life. Here again are the measures for clinical trials, which are the same as cohort studies. And we reviewed those already: the relative risk, attributable risk, and number needed to treat or harm. I'd like to spend a minute talking about the intention to treat analyses. These are often done in clinical trials, and what it means is that the analysis is done on the subjects as they were randomized initially, regardless of compliance with the assigned protocol. So if they cross over from one arm of the study to the other, if they originally are put into the group that's going to be treated medically rather than surgically, and they end up having surgery, they would be analyzed in the medicine-only arm of the trial, as if they were still in that arm, even if they had surgery done, even if they crossed over. This is conservative analysis in the sense of it's less likely to find an effect if there really is one there, because some of the people from one arm actually ended up getting the treatment that was in the other arm, so it's not as clean. But it's generally preferred because if you don't analyze it this way, then it becomes more like a cohort study. So if people end up going into the surgery trial, then they're self-selecting more. And if you analyzed it that way, the randomization would no longer apply as cleanly. So it becomes more like a cohort study. The experimenter loses control over who goes into which group. So in general, most of the clinical trials are analyzed with this intention to treat analysis. Survival analysis is oftentimes the way clinical trials are analyzed, and what this does is it plots or lines up the times of exposure for the different subjects, and in that way it's analogous to the person-time incidence that we talked about in the cohort studies in the last unit. It's useful when follow-up periods vary widely and often analyzed with this Cox proportional hazards model. I want to touch briefly on some variations in clinical trial designs. There's a factorial design that basically adds additional studies within the study. So once the subjects are randomized to group A or B, and I'll show you this in more of a diagrammatic way, then they are again randomized into additional subgroups in order to do additional analyses. So it basically is adding other studies within the study. There's a crossover design. Now this is not to be confused with crossovers that happen within a clinical trial that we had just talked about. This is intentional, and what it does is it takes subjects, gives them one exposure, and then crosses them over intentionally so that they then get the other exposure. What it does is it adds a lot of power because you're using the same subjects for both interventions, so you know that all of the subject characteristics are the same in each group. So you can get by with very few subjects because the power is quite high. So you might do a trial of inhaler or placebo, somebody who has ongoing asthma symptoms, and you can give them the inhaler or placebo, let them use it for a while, and then switch the same person and then see how they do. So you can get by with sometimes 10 or 12 subjects. Then there are meta-analyses. This is not limited to clinical trials, and it adds power by adding up studies together, and we did touch on that earlier. It adds power by increasing the subject size that may not be available in the individual studies. Here's a diagrammatic illustration of the factorial design. You start out with a study sample, say of 1,000. You might randomize into intervention A or the control group, and so you'd get about 500 in each of those groups. And then you might further randomize each of those groups into 2 additional subgroups, and you could do additional studies on those. Again, it's a way of adding additional studies or sub-studies into the study. Here's a diagrammatic illustration of the crossover design, starting with the total study sample, and perhaps randomizing to experimental or control groups, for example, with the inhaler or placebo for people with asthma. Then after a time of monitoring, you have stop the placebo or the inhaler, have a washout period so the effects go away, and then switch them over and start them in the opposite arm of the study and follow them for a time again. Here's another illustration, this time using a depression drug or placebo. You could randomize them to get the drug or placebo, see what effect it has, stop the medication, have a washout period, and then have them in the other group. Again, you can get by with very few subjects with a study like this because the power is so high, because the variability between groups is so low, related to the fact that it's the same people getting both the experimental intervention and the control intervention, or lack of intervention. Here's an example of the meta-analysis, and it's the same one used earlier, but just to remind you that if you add up the studies and look at the diamond near the bottom, you've got a smaller confidence interval, more power, more ability to see a difference if there's really one there, than looking at the individual studies above, which oftentimes don't have enough subjects and have wider confidence intervals and therefore cross one and don't show an effect. The last concept I want to talk about with clinical trials is that of community trials, which are clinical trials with the community as the unit of allocation and analysis. These are useful in that they are more real life, more what really happens. They're more effectiveness trials rather than efficacy trials. They include social context. So, for example, studies on problem drinking or effects of seatbelt laws, those things affect people other than the subjects themselves, and so you can look at the societal context or the community context. The difficulty is they're hard to control in terms of differences between different communities. There's a lot of micro differences that you can't account for very well or measure. Also, you have to be aware of the ecological fallacy that we talked about earlier, attributing individual differences based on population data. In Unit 8, we covered a lot of aspects of clinical trials. We looked at the design, the appropriate use, advantages and disadvantages of that study design. We looked at the biases that would be related to the design. We looked at the concept of blinding, confounders, which is what clinical trials that are randomized eliminate, and that's what makes them so powerful. We looked at how increased control means decreased generalizability. We looked at common measures used in clinical trials, survival analysis, the intention to treat concept, which is quite important and commonly used. We looked at factorial crossover and meta-analysis trials and community trials. And one concept that I would like to just bring in here, because I think it's very important, it's really critical in clinical trials, is to not forget, is the power. If you have a negative clinical trial, you really should ask the question or look for the answer to the question of what was the power of the study to see the difference, if there really was a difference. Because if you don't look at enough people, if you don't have enough power, then a negative study is really not very powerful. It doesn't convince the reader that there isn't an effect, because there wasn't enough power to see one had there been one there. So if you have a clinical trial and it's negative, look in the discussion section, usually it's in the discussion section, and see what the authors planned on or thought about the power of the study. They should convince you that they looked at enough people to see that difference if there was one there. That's it for Unit 8 and for all of the units in terms of the PowerPoint presentations. So good luck with the rest of this unit and the course. Good day.